Hello. So in this lecture, we will be talking about Thevenon's theorem. So this will be the last, or the second to the last theorem that we'll be discussing in chapter one. The last will be the Norton's theorem. And again, to illustrate Thevenon's theorem, we will be using our previous example, just the example we did from the first theorem that we discussed. And this time, we will be calculating for the current passing through Z2 or I2 to illustrate the concept of Thevenon's theorem. And again, the Thevenon's theorem is still the same concept as in the same as in the circuits one. The procedures are also the same. So to solve this, so solution. So the first step in applying Thevenon's theorem is to solve for the looking back resistance or impedance. In this case now, we'll be talking about impedances instead of resistances because we have now included the capacitance and the inductance in the circuit. So instead of RTH, we will be solving for ZTH. And to do that, the rules are to remove all the voltage sources or replace all the voltage sources by their internal impedance if there is given internal impedance. But if there's no internal impedance, then just replace it with a short circuit. So in this case, so we have here Z1, or Z1 is a capacitor, negative J4. Then just draw a capacitor. Then that EA, we will replace that. We remove that and replace that with a short circuit. Then we also remove the load. So our load here will be Z2 because we are solving for the current passing through Z2, which is I2. So we make Z2 as our load. So just remove that and replace it with an open circuit. Then for the right side, we have, let's do that again. So we have a resistor, 5 ohms, then replace the voltage source with a short circuit. And the impedance at that load that we remove will be our ZTH, or the looking back resistance or impedance. So to solve ZTH from this circuit, this is a simple parallel circuit. Negative J4 is in parallel with 5. So to solve for ZTH is just equal to the parallel combination. So J4 times 5 all over 5 minus J4. So therefore, ZTH will be equal to, so we have negative 4 J4 times 5 all over 5 minus J4 equals, or it should be minus J4. Negative 5 minus J4. So we have 3.123 angle negative 51.34. Negative 51.34 degrees. So the unit is ohms because this is impedance. So after solving for ZTH, the next step is to determine now our voltage, VTH. And we bring back our sources in the circuit. So bring them back. But still, don't bring back the load. And 5. So this is negative J4. This is 5. And this is our load. This is actually 100 plus J10. 100 plus J10. And this one is 100 minus J5. 100 minus J5. And VTH is this voltage at this point. So this is plus minus. So you can use any method you want to solve for that voltage. But I think the easier way to solve this is to use nodal analysis. We just equate, because the current, remember, VTH at this point, the load was removed and replaced with an open circuit. So there's no current. There's no current passing through this branch here. So if there's no current passing through there, then the current passing through here, I, will be just equal to the current here. So we just equate that current, then solve for VTH. So what is the current at this point at negative J4? So remember, the voltage here is VTH. The voltage here is 100 plus J10. So that current is just equal to 100 minus plus J10. So that's the voltage here. Then minus VTH. Then we divide that with the impedance, which is negative J4. And this is the current I. And it is equal to the current also here. So the voltage here is still VTH. So we start with VTH, then minus the voltage here, which is 100 minus J5. So this will become minus 100 plus J5 all over the resistance 5. And the only unknown here now is VTH. You can also use Maxwell or mesh analysis if you want. You can apply meshes at these points or loops. Then there will be two unknowns, the current and the voltage VTH. So you can use any other method that you want. Then simplify and solve for VTH at this point. So we can divide 100 plus J10. So we have 100 plus J10 all over negative J4. So we have 25.125 angle 95.71. Then this is negative 1 VTH divided by negative J4. So negative 1 divided by J4, negative J4. So negative J4. That will be 0.25 angle negative 90. So plus 0.25 angle negative 90. This is VTH times VTH. To the right side, we have 1 over 5 is just 0.2. 0.2. Then times VTH. Then for this one, we have negative 100 plus G5 all over 5. 20.025. So plus 20.025 angle 177.14. 177.14 degrees. Then we can put this negative 90.25 on the right side. Then we add it with 0.25. So we have VTH times 0.25 minus 0.25 angle negative 90. So this is 0.354 angle 45 degrees. Then at the right side, or this should be 0.2 instead of 0.25. It's 0.2 minus 0.25. So this should be 32 and 51.34. 32 and 51.34 degrees. And to the right side, we can move this one 20.025 and we retain this. So this will be 25.125 angle 95.71. Then we subtract our angle here, or 20. This is 20.025 angle 177.14. Press equals. So we have 29.704. 29.704 angle 53.903. 53.903 degrees. So BTH now will be equal to that answer divided by 0.32 angle 51.34. We have 92.82. 92.82 angle 2.56. 2.56 degrees volts. Now that we solve the looking back impedance GTH and VTH, so the circuit is now Thevenized. We convert this one into the Thevenin circuit, and it will look like this. So we have the voltage VTH, then we have an impedance, which is the ZTH. So this is the equivalent of that circuit when we remove the load. Then to solve for the current that passes through our load 3 plus G4. So we just bring back that load and we connect it again at this point. So this point, if this is A and B in the circuit, this is also A and B. A and B. This is A and also B. So if we bring back that load, and that will be this circuit. Now, if you want to determine the current that passes through here, which is I2. So it's also the current here. This is also I2. So it's the total current. So if you want to solve for the total current, it's just equal to I2 is just equal to the total voltage, which is VTH, divided by the total resistance or impedance, because this is in series. So we just add them. So ZTH plus the load plus ZL. So we already know VTH. VTH is 92.82 angle 2.56 degrees. We divide this with our ZTH. Our ZTH here, this is 3.123 angle negative 51.34. Then we add our load. Our load is 3 plus J4, ZL. Then compute for I2. So this should be 92.82, 2.56 all over 3.123. Angle negative 51.34. Then we add our load. That is 3 plus G4. And this will be the result. 17. So I2 is equal to 17.88 with an angle of negative 14.94. Negative 14.94 degrees ampere. So if we check if our answer is correct, we can check our previous answer. So this is our previous answer, 17.87. There's a bit discrepancy with the, maybe that is due to the round offing. Here we also have I2 17.87 and here 17.87. Okay, so this is how we used Thevenin's theorem to in AC circuits.